As promised, if you're following along with these lessons in order, I am now going to embark in a discussion of oxidation and reduction in the context of organic chemistry. So in the previous lesson, I stated that the following reaction, starting with a secondary alcohol and forming a ketone, is an oxidation. How did I know that? And what reagent needs to go above the arrow? So in this series of lessons, we're going to consider the answer to these two questions. Oxidation and reduction are familiar topics from general chemistry, but we're going to look at them in an entirely new way here. So for the moment, I would actually like you to forget everything you know about this topic, learn some new rules, and then in the end, I will show you how the organic definitions of oxidation and reduction tie into the general chemistry definitions. So what are my definitions? Well, what we have to do in this lesson is consider what organic chemists mean when we talk about oxidation states. So we have to fundamentally figure out how to assign an oxidation state to a particular carbon atom. So the way you do this, since this is a case in which our carbon atoms are participating in covalent bonds, you start at 0. Okay, that's defined as the oxidation state for an element in all of chemistry. So start by making believe you have an elemental carbon and start with 0. Then add 1 for every bond to a more electronegative element, and subtract 1 for every bond to a less electronegative element. So this will only become clear by looking at some examples. We will start with a very simple organic molecule, methane Ch4. So we start with 0 for carbon and say there are 4 bonds to hydrogen. And here's what's really important. Hydrogen is less electronegative than carbon. So anytime you have a bond to a hydrogen, you have to subtract 1 from the oxidation state. We don't say that the electronegativity difference is big enough to make the bonds polar, but it is there, it is real, and in order to make the bookkeeping work, you have to remember that every hydrogen results in a -1. So we have 4 bonds to hydrogen, therefore the oxidation state of carbon in this molecule is -4. On the other end of the spectrum, let's look at carbon dioxide. In fact, burning natural gas to produce heat is the process by which you take methane and turn it into carbon dioxide, and this is the most efficient combustion process that can happen to a source of fuel. You're going from the lowest possible oxidation state to, in this case, as we shall see, the highest possible oxidation state for carbon. So in this case, in carbon dioxide, carbon is forming 4 bonds to oxygen. Okay, so when you have a double bond, you have to count each bond to oxygen as being separate. So there are 4 total bonds to oxygen, and therefore the oxidation state is +4, because of course oxygen is more electronegative than carbon is. So the oxidation state range for carbon is from -4 to +4. Okay, then we have all of what we call the intermediate oxidation state. So let's look at some examples of some molecules that are somewhere in between. How about methanol, a primary alcohol? Well, going through the same rules, we have 3 bonds to hydrogen. That would take us down to -3, but 1 bond to oxygen, that's going to add 1, so that leads to a net oxidation state of -2. We can also do the same analysis to molecules that contain more than 1 carbon. Initially, for this first example at least, we're going to evaluate the oxidation state at each of the 2 carbons. Okay, so starting with the CH3, we have 3 bonds going to hydrogen. That's going to take us to -3. The 4th bond is to a carbon. Well, carbon has the same electronegativity as carbon. Therefore, this is going to have no effect. So the oxidation state for the CH3 carbon is -3. For carbon 1 that actually contains the alcohol, we have 2 bonds to hydrogen. That's going to take us to -2. We have 1 bond to oxygen. That's going to increase us by 1. So that takes us to -1. And the 4th bond is to a carbon. That's going to have no effect. So the oxidation state for carbon 1 is going to be -1. Now, it is a general rule that a CH3 bound to another carbon will always have an oxidation state of -3. Okay, let's keep going. Aldehyde. The CH3 we're not going to worry about. That's always going to be the case. But what about the carbonyl carbon? Well, now we have 1 bond to a hydrogen, which will take us down to -1, and 2 bonds to oxygen. That raises us up to +1, and the CH3 has no effect. So the final answer is +1. Carboxylic acid. We now have no bonds to hydrogen and 3 bonds to oxygen. That's going to give us +3. The other bond here is to another carbon. That will have no effect. So our answer is +3. What about molecules? Okay, we're considering right now oxidation states at individual carbon atoms, but in order to understand oxidation and reduction reactions, we have to come up with some way to look at what's happening to an overall molecule. So my definition of oxidation state for a molecule is that it is the sum of the oxidation states of each individual carbon atom. So just looking at a couple of the examples that we've already looked at, if we look at the acetaldehyde, we initially evaluated the oxidation state of the carbonyl carbon to be +1. We know that a CH3 is always going to be -3. So the overall oxidation state of this molecule is 1 minus 3, which is -2. What about ethanol? We have 1 carbon with a -1, the second carbon with a -3. We add these together and we get a total oxidation state of -4. Okay, so now in the next lesson, we're going to use these definitions to identify when a reaction is an oxidation reaction, when a reaction is a reduction reaction, and when it is neither.